Okay, good. So welcome again, everybody. It is my pleasure this week to introduce my colleague on the Bar-Ilan University faculty, Professor Igal Milchtaich, who is an excellent researcher and also a very good photographer. So you should all at some point ask him to see some of his great photographs. And with that, I give it to you, Igal. Go ahead.
Thank you. Welcome everybody to my talk. Let me share my slides with you. So this talk is about best response equilibrium, which is a generalization of Nash equilibrium. Let me give you a rough idea of the underlying principle. So let's start with a simple and very attractive game where the player gets whatever he wants. He chooses the payoff. How much should the player choose? 1,000? Well, 1 million is better than 1,000, and 1 billion is better than that. So what's a rational strategy? Surely each of the numbers by itself is not a rational strategy. But what about the whole sequence? Is the whole sequence a representation of a strategy? Is that a good strategy? It might be, since the payoff increases to infinity, which is the supermoon. Does that mean that it is an equilibrium strategy? And what kind of strategy is that? Surely not a pure strategy, since a pure strategy is just a choice of action. Is that a mixed strategy? A mixed strategy is about probabilities. So what probability do we assign, say, for each of the individual elements of the sequence? Well, the probability must be 0, for otherwise we forego some opportunity to make a higher gain. But then by additivity, we get that the initial segment of the sequence, any initial sequence, has probability 0. And this means that we cannot have sigma additivity, because then the whole sequence would have 0 probability, which is not what we want. However, if we are content with finite additivity, then we do have a well-defined probability measure here, which is the following. For a subset of the rational numbers, we assign probability 0 if the set includes at most finitely many of the numbers specified, the elements of the sequence. And if the complement of the set has this property, then we assign it probability 1. Obviously, this does not cover the entire power set of the real line, but that's a minor problem since we can always extend it to the entire power set. And that strategy describes a rational choice of action in the following sense. First, it's clear that no single action is optimal, since the supermoon of the payoff is infinity. What strategy sigma does is to exclude the choice of actions yielding low payoffs, no matter how we define low payoff. So formally, for any a less than the supermoon, which is infinity here, the set of all choices, all actions, which yield less than a has probability 0. And that's because the limit of the payoffs in the sequence is the supermoon, which is infinity, which by definition of limit means that only finitely many SNs can give less than a. So the condition specified here is satisfied. And using this expression as a definition, we'll say that sigma is a best response equilibrium in this single player game. And such an equilibrium exists in every one-player game. And I just showed you the proof. The construction we use works for any action set and any pair function. And even though the action set here, which is the V line, has structure, it has many structures, we didn't use any of them. We could use a structure and define the equilibrium strategy as sigma infinity, which roughly means choose infinity. So what this means formally is that any set which is bounded from above is assigned probability 0, and its complement, which is a neighborhood of infinity, is assigned probability 1. So that would be an alternative. Actually, it's a restriction of the strategy we just defined that makes it more intuitive. And that's the idea of a best response equilibrium in a nutshell. Of course, the challenge here is to extend this in a meaningful way to n-player games, to real games. Are there any questions about the single player case? So let me be a bit more formal here. Consider any set S and its power set, the set of all subsets of S. A collection of subsets, script A, is an algebra if it's closed under taking complements and finite unions. And we'll say that these sets are the measurable sets. A finitely additive probability is a function that assigns a number between 0 and 1 to each of these sets, such that additivity holds, finite additivity, and the entire set has probability 1. Now, probability in the usual sense adds the requirement of sigma additivity, which is for any sequence of disjoint sets whose union is measurable, we have the usual equality. And we say that the one finitely additive probability, script A prime, is an extension of script A if it just extends the latter to a larger algebra. And a total extension is one which is defined on the whole power set. Now, one function which is defined on the entire power set, but is not an extension because it's usually not additive, is the outer measure. And this is defined by looking at measurable sets that cover a given set A, looking at their probability and taking the infimum. And if this infimum is 0, then this is called a null set. Now, once you have a measure, you can define integration. As usual, we start with simple measurable functions, which take only finitely many values, whose inverse image is measurable. And then you define integral of such functions in the usual way. And you extend this to functions which are called mu-integrable, which are the limit in probability of a sequence of simple measurable functions, which also satisfy an additional condition that is needed only if f is unbounded. And then you define the integral of f as the limit of the integrals of these functions. And this is well defined, doesn't depend on the sequence, and it's finite. And the last thing that we need is to define product of probabilities. Suppose you have finitely many finitely additive probabilities, each with its set and algebra. And I look at the product algebra, which consists of finite unions of measurable rectangles, you define the product measure as the product of the sides of each rectangle, and that gives you a product algebra and product probability. And now a small lemma is that if the function is bounded and you compute the multiple integral, which is the integral with respect to the product probability, it is equal to the iterated integral, where you integrate over S1, then over S2, and so on, provided that all the integrals here exist. Which means in particular that the multiple integral does not depend on the order of integration. So all this looks familiar, but it's actually not, because Fubini's theorem does not hold for finitely additive measures. So it's possible that only one or the other of these integral exists.
Igal, would you mind
Yes.
going back one slide? Thanks. So I'm looking at the definition of an integrable function. So the sequence Fn. So okay, so you require that the limit of the outer measure of the set of points where Fn differs from F by more than epsilon. Okay, that the outer measure of the set goes to 0.
Right. This is just convergence in probability.
And if you interchange, just out of curiosity, because this is very subtle, a definition, if you interchange mu star and the limit, so and you would require that the set of, basically would require that the set of points where Fn converges to F pointwise is null. That wouldn't be good.
I'll have to think about that.
Okay, so it's not obvious.
It's not obvious to me right now, at least.
Okay.
Maybe it will become obvious if I think about that, but right now, no.
Thank you. Okay, thanks.
Igal, can I also ask something here, maybe?
Yes.
I think I used to know it, but it's been some time about the time I was working on this finite additive measures. Your integral definition, I believe that, but maybe my recollection is not correct anymore. It's the same as saying that the lower integral is the same as equal to the upper integral when you approximate it with the simple functions from below and from simple functions from above, right?
Yes, for bounded function, this is correct. So the integral exists if and only if the upper and the lower integral are equal, and then the integral is, of course, their common value. Okay, but it is defined also for unbounded functions.
I see. That makes it clear. Okay, right. That makes a big difference here. Okay, thank you. This is clear. Thank you.
Sorry, Dan. Sorry, Igal. So the outer measure was defined by the finite covering, or
you cover by a single set. So you look at a single measurable set that cover.
Yeah, but you had a field, so an algebra, so this is a finite cover. Okay, thank you.
Okay, so now let's get to business, which is the definition of equilibrium, which is the following. So first you take any game. There are no assumptions whatsoever on the action set. There's no structure to the action set, as there's no assumption about the pair function. The actions are pure strategies. Now, what's a mixed strategy? A mixed strategy, or just a strategy, is only any finitely additive probability defined on any algebra. So one somewhat important point here is that the algebra is not given. It is part of the definition. Often, actually usually, when you talk about the mixed extension of the game, the mixed extension specifies the measurable structure for strategies, which, if you think of it, is somewhat strange, because if, say, the game is finite, you just choose a number, and then for the mixed extension, you come up with Borel sets and things like that, which have nothing to do with the game at hand. Here, the algebra is part of the solution concept rather than of the game. I wouldn't like to make too much of this point, but it is a somewhat important point, also technically. And if you have a profile of strategies, then you may look at the product probability and identify it with a strategy profile, or you may also only look at products of the strategies of players other than some player I and consider that an I's strategy. So here's the definition of best response equilibrium. It is a generalization of Nash equilibrium. First, because strategy here is generalization of mixed strategy. And second, because the best response requirement is satisfied in the case of Nash equilibrium. So here's the definition. A strategy profile is the best response equilibrium if it satisfies two conditions. First, for every player I and action of that player, the following integral has to be well defined. It should exist. And what this integral gives you is just the expected payoff of player I if he chooses action Si. So the integration is with respect to the others' strategies. Now, there's a well-defined notion of what player I gets from choosing each action Si. And we want him to choose rationally, which means the following. For every A less than the supremum of what he can get, the outer measure of all actions yielding less than A is 0, which says that sets of low payoff actions are null. This is the best response requirement, which is the heart of the definition. Is the definition clear?
Igal, what is the difference between this definition and just an equilibrium with finitely additive probabilities?
You mean Janusz Flash and al?
For example.
Yes, of course, I will get to that. My work is inspired by my work. So I have to point out the differences, and I will. So just bear with me. If you stay till the end, you'll get the answer. It's almost at the end.
Igal,
yes.
You said that the algebra is part of the definition of strategy, but where does it appear here?
In the strategy profile. The strategy profile specifies a strategy for each player, and as part of the specification of the strategy, the algebra is given. Does that make sense?
I'll have to think of it. Okay, well, I'll think of it and I'll get back to you.
Okay, let me...
Igal, sorry,
yes.
Igal. So usually in this charge or finitely additivity business, the problem is that the function you would like to integrate is not integrable. So I don't see in the definition that UI is integrable.
Well, yes, that's a good point. So the answer is that the definition goes halfway. You integrate with respect to the others' strategies. So, for example, if it's a two-player game, then the first part of the definition holds automatically, so to speak. And integration with respect to all the strategies is not part of the definition. That's an important distinction between this and other definitions. So with two-player games, you don't have any integrability problem whatsoever, even though the integral with respect to the project measure does not necessarily exist. Let me expand on that.
Okay.
So one remark is that if the utility function is bounded, or even if V, which gives the pair for each, expected pair for each player, each action of player I is bounded, then there's an alternative presentation of the best response condition, which is quite familiar, which is the expected pair equals to the supremem. Now the expectation here on the left-hand side, and this is an answer to Miklos, this is a iterated integral. So Vi is itself an integral with respect to the others strategy, and here you integrate with respect to the player's own strategy. And the equilibrium condition is equivalent to the requirement that this iterated equilibrium is the supremem. Now the equilibrium pair would be the multiple integral, and it may not exist, but that's not a problem. If it does not exist, then there's no well-defined equilibrium payoff, but there is a well-defined equilibrium, and the equilibrium is defined by the condition that low payoff action are excluded. So you see that to define equilibrium, you don't have to have expected payoff, which again is somewhat unorthodox, because in the mixed extension, you start with looking at expected payoff for any strategy profile, and you have to say whether you can improve it unilaterally. A second,
Igal, I'm sorry. Would you mind going back one slide one more time for me? Thanks. The first condition, so it's satisfied automatically in 2-player games, and say in 3-player games, it would basically mean that you can change the order of integration, right? Is that what it means?
Yes, that's a very penetrating remark. That's correct, and it may not hold. So that means that in 3-player game, an equilibrium may not exist. And I'll show you an example if I have time.
Thank you.
And another remark is that if you have an equilibrium and you extend it, that is, you extend each of the strategies to a larger algebra, it's still an equilibrium. And you can always extend it to the entire power set. That's a consequence of the Hahn-Banach theorem. So the equilibrium becomes total, which means that in principle, you don't have to deal with algebras at all. You can always look at the entire power set. So the algebra becomes unimportant. But in practice, you certainly do not want to define strategy for the entire power set. And what this proposition says is that you have to define it for a rich enough algebra, and then you're done. Anyway, in principle, there's no loss of generality in assuming that probability is defined for any set of actions, and therefore you also don't have the outer measure, because the outer measure is the measure itself. Let me give you a number of examples that show how it works. First example is bilateral trade. So you have a seller and a buyer, and the item is worth nothing to the seller and one to the buyer, who has to offer a price. So it's a take it or leave it offer. And the strategy for the seller is to choose the set of acceptable prices. Now, one attractive strategy is accepting any positive price. And this is a weakly dominant strategy. But strangely enough, it's not a Nash equilibrium strategy, because there are no best response to it. How much do you offer if the other guy is willing to accept any positive price? Well, in one sense, the answer is obvious. What's the answer? Well, I ask my students and they say offer an epsilon, which is the correct answer. You should offer an epsilon. What does it mean to offer an epsilon? Well, here's what it means. It's the strategy of delta 0 plus, which is a finitely additive probability, which assigns 1 to a set that includes a right neighborhood of 0, and 0 to a complement of such a set. And this strategy together with the strategy of accepting any positive price, is an equilibrium, a best response equilibrium. And the pairs in this case are well defined. They are 1 to the buyer and 0 to the seller. And here's another example, price competition. You have n identical firms with the same cost function, and they set prices. And those that are tied for the lowest price P share the demand, which depend on P, equally. Now, usually with price competition, the competition is expected to drive the price to the marginal cost. But with best response equilibrium, this is incorrect. Another problem is that a Nash equilibrium may not exist, even in a duopoly. And here's a well-known example. The demand is just linear, and the costs are quasi-fixed, meaning that they are 0 at the origin and fixed outside the origin. And here there's no Nash equilibrium in the usual sense. Now, if we look at this problem and start with the monopoly profit, then it looks like that. Let me draw it for you. So that's the price, and this is the profit for the monopoly, and it looks like that. This is 0.2.
Maybe it's just me, but I don't see the lower part of the slide.
You don't see the lower part of the slide?
Could be.
Do others see the lower?
Nobody else has a problem, then it's.
I see, yeah.
Sorry, then it's just me.
So it looks like a local problem. Maybe in your side of the channel, things are more complicated. So that's the monopoly profit function. And now, here's the point. For any price P, there's a best response equilibrium in which they both offer P minus epsilon. And why is that an equilibrium? Because let's draw the V1. V1 is the function that gives the payoff of, say, player 1 as a function of what he offers. So the other guy is offering P. This is P. And if he offers less than P, then he makes a sale, and he's a monopolist. So it goes like this. And if he offers more than P, then his price is higher, and he doesn't sell anything, so he's here. And if he offers exactly P, still he's outbid by the other guy who's offering P minus epsilon. So that's how V1 looks like. And the top here is the supermoon. So how much should he offer? Well, P minus epsilon, and then reap effectively all the profit. So this proves that this is indeed the best response equilibrium. And it's quite easy to see that there's no well-defined equilibrium profits here, because in effect they are both sure that they will get the sell, which is impossible. But it is nevertheless an equilibrium. And this structure can be generalized very easily to any n-player game like that. So there is a best response equilibrium where they offer P minus epsilon, where P is any price with these properties. You look at the monopoly profit function and choose some P such that the profit increases between 0 and P and it's non-negative, and any P like that gives an equilibrium. So that's a very general construction, and you can also extend that to asymmetric games. And essentially, this is an example. This example was by Vasquez. He showed essentially that example and demonstrated how these P minus epsilon strategies can be used. Any question about this example? Another example is spatial competition with 3 firms. So each firm chooses a location on the unit interval, and the consumers who are uniformly distributed choose the closest firm, who gets a profit, which is the total mass of the consumers choosing it. It is well known that with 3 firms, there is no pure strategy equilibrium. It is also known that there is symmetric Nash equilibrium where the strategy is uniform between 1/4 and 3/4. It is also known that there is a unique equilibrium up to permutation of players with a mixture of pure and mixed strategies, which is the following. One firm chooses 1/2, and the other 2 use the same mixed strategy, which is, I suppose, slightly larger than before. And it's highly non-uniform. Most of the mass is near the edges. And the interesting point here is that you cannot replace that by randomization, say 1/4 and 3/4 with probability 1/2. That doesn't work. However, you can replace it by 1/2 quarter minus epsilon and 1/2 3/4 plus epsilon. That does work. That gives you a best response equilibrium. And in this equilibrium, only the guy choosing 1/2 has a well-defined equilibrium payoff, which, depending on x, is between 1/3 and 1/2. And the last example I'm going to give is a zero-sum game without a value. This is a classical example. Here, the 2 players have action set, which is the unit interval, and u is this function. So the function is 0 on the diagonal, 0 in a line parallel to diagonal, and elsewhere it's either 1 or -1. And here the max min and the min max are unequal. The maximum value is 1/3, and maximum strategy is putting weight 1/3 at 0 and 2/3 at 1. So you see that if player 2 chooses 0, then the payoff is 2/3. And if he chooses 1, then the payoff is 1/3. And in between, it doesn't go below 1/3. And the minimax value is 3/7 with this minimax strategy. So there's no equality between the 2 values, and therefore there's no Nash equilibrium mixed strategy. However, there is a strategy of player 2 which lowers the maximum payoff of 1 to 1/3, and this is also an example by Vasquez. And the strategy puts a weight of 1/3 just below 1/2 and 2/3 at 1. So if player 1 chooses 1, then the payoff is 1/3. And if he chooses 0, the payoff is still 1/3, because the lower mass is at the -1 area, and in between it never goes above 1/3, which means that the strategy profile of the last strategy and sigma 1 is a best response equilibrium, and there are well-defined equilibrium payoffs, 1/3 and -1/3. That was the good news part. Now, the bad news, which are that an equilibrium does not always exist. So here's an example of a 3-player game that does not have an equilibrium, best response equilibrium. The action set is the open unit interval. For player 1 and 2, the payoff is the negative of their choice. And for player 3, it's this function of only the other guy's choice. So in the unit square, it has the value 1 above the diagonal, and below the diagonal, it goes linearly with S2 to 0. Now, the best response requirements for players 1 and 2 are that their expected payoff is 0, and they can get that by choosing epsilon. And for player 3, the payoff does not exist. And this is because, as Arkady anticipated, is that the iterated integrals exist, but they are not equal. One of them is 0, and the other one is 1. So no equilibrium here, because there's no well-defined payoff for player 3. Now, for two-player games, this is not a problem. This is never a problem. But you may have a problem with the second equilibrium, which is the best response equilibrium. So here's an example showing this. Their action set is the set of natural numbers, and this is the payoff matrix. So you see that if player 1 chooses more than what player 2 chooses, they both get their choices. Otherwise, only a player that chose 1 gets his choice. And here there's no equilibrium. And here's the argument. And this is similar to an example given by Janusz and co-authors. And let me give you just one half the proof. Suppose that strategy S sigma 2 is diffuse in the sense that it assigns probability 0 to every number, which means that if player 1 chooses 1, then he gets 1, and for each of the other choices, he gets 0. So he should choose 1 for sure. But if he chooses 1 for sure, then player 2 should choose also 1 for sure. So his strategy is not diffuse. So you have a contradiction. And in the other direction, you also have a contradiction, which shows that there is no best response equilibrium here. So the existence of equilibrium is not guaranteed. Any questions about this example? So now I get to the last part, which is the comparison of these solution concepts with other solution concepts. The idea of using finitely additive probabilities is quite old. And the problem of using finitely additive probabilities, which is non-integrability of payoff functions, has been tackled before. So for example, Janowskaja presented a finitely additive extension for zero-sum game, and she solves the problem of non-integrability essentially by inventing some value that the integral takes. Another solution concept is optimistic equilibrium of Vasquez, and the price competition example is essentially his. And why is that optimistic? Because both firms are optimistic about their prices being lower than the competitor's price, even though they use the same strategy. Now, with best response equilibrium, this optimism is not present in all examples. For example, consider a game where the guy asking the highest number wins. So there you have a similar equilibrium, but the interpretation is the opposite, that they are optimistic, that they use the same strategy and nevertheless believe they often will be highest. So optimism or pessimism is not the important feature here. Next is the legitimate equilibrium of flesh and quarters, which is the one most similar to my notion, and is defined as following. It's a strategy profile such that for every player I and every alternative strategy tau I, the upper integral of the utility, which is defined as the infimum of the integral of simple measurable functions greater than the utility function. Now this expression gives what the player thinks he gets when everyone uses S. So in a sense, he's optimist. When he's considering an alternative, tau, suddenly he becomes a pessimist. Now he looks at the lower integral, which is the supremum over the integrals of simple measurable functions less than the utility function. And here the pair function is assumed bounded to have well-defined integrals. And also, quite importantly, the algebras are given. They are part of the game rather than part of the solution concept. And an important feature of this notion is that an equilibrium always exists, which is not the case for best response equilibrium. And the reason for this difference is that best response equilibrium is a more demanding notion in the following sense. Every best response equilibrium is a legitimate equilibrium, but not conversely. So that's true only for bounded functions, pair functions. Otherwise, legitimate equilibrium is undefined. So there's a difference there. However, there are also both conceptual differences, general conceptual differences, and differences in content, in predictions. So let me give you an example of a difference in prediction. So here's the game. It's a single player game. Has to choose a number between 0 and 1, and he gets 1 if it's a rational number. And the algebra, which has to be fixed, let's fix it to the finite unions of subintervals. With this algebra, a simple function satisfies that it's less than the pair function if and only if it's 0 outside some finite set of rational numbers, and it's greater than the utility function if and only if it's 1 outside some finite set of irrational numbers. Now, one strategy for the player is to choose 0 with probability 1. And since this is a rational number, he gets 1. So he should also get 1 without deviating to this strategy. And the condition for legitimate equilibrium is that the measure of each singleton is 0 if that singleton is an irrational number. So every single irrational number has to have probability 0. And that's the whole condition. If this is satisfied, then sigma is a legitimate equilibrium. So what would be an example of such a strategy? Well, Lebesgue measure is one. Any non-atomic probability assign probability 0 to any singleton. And I believe that in some sense this is the wrong answer, because Lebesgue measure means choose a number at random, which should be wrong, right? Because there are only finitely many rational numbers and infinitely many, uncountably infinitely many irrational numbers. So it can't be that you can choose at random. If you look at the condition for best response equilibrium, this is a strong condition, and it says that the outer measure of the irrational number should be 0, which is equivalent to the condition that the sum of the masses of the rational numbers is 1. And this is equivalent to the condition that your strategy is a restriction of some Borel, that is sigma additive, probability measure which is supported in Q. So this condition is necessary and sufficient for best response equilibrium, and it is much stronger than the condition for legitimate equilibrium. Any questions about this example? So let me finish by summarizing the more conceptual issues. I touched on some of them during the presentation. Let's start with thinking about mixed Nash equilibrium. A mixed Nash equilibrium, a feature of mixed Nash equilibrium is that it excludes the choices of suboptimal actions. Suboptimal meaning not best response. And this condition is necessary. It's a feature of any mixed Nash equilibrium, but it's also sufficient. If the probability is assigned to the suboptimal action is 0, then you have a mixed Nash equilibrium. And here you only consider the support of the player strategy, so of the mixed strategy. So actually, for this to be a mixed strategy, it doesn't matter what probability is assigned to each of the optimal actions. And in particular, to define the mixed strategy equilibrium, there's no need to consider alternative mixed actions. And so the mixed extension, which is the extension of the game where the players choose mixed strategy rather than a pure strategy, is not needed for defining mixed Nash equilibrium. And in this work, we do away with both the mixed extension and the idea that there are alternative mixed strategies. In addition, mixed strategies here are not randomized strategies. And since they are not randomized strategies, they are not supposed to be playable, their meaning has to be thought about. And the best I can describe my thoughts about the interpretation is that the strategies defined what others are expecting the players to do. This is, I know it's a rough description, but I think it catches much. This is an assessment, this is an outside assessment of what the players will do. However, everyone knows that the player is rational, so they would not assign him the choice of bad strategies. The strategy describing the player has to be such that all actions that are yielding low expected pairs are to be excluded. And here, expectation is with respect to the other strategies. So the interpretation is that the player has no better knowledge of the other players than our observer has, right? The player may know what he's going to play. It doesn't randomize. He's going to play something. He has a very good idea of what he's going to play, but his notion, his knowledge of the other players' actions is the outside observer's knowledge. And since expectation here is only with respect to the other player strategies, integration with respect to probability is irrelevant to the players. Since the players, as I mentioned, know what they're going to play, so there's no need for them to mix with respect to their mixed strategy. And therefore, the existence of this integral, which is the expected payoff, is optional. We have a well-defined notion of equilibrium, even if this does not exist, and therefore it can be done away also. And these are the underlying quasi-philosophical notions of best response equilibrium. And with this, I conclude.
Okay, great. Thank you. Are there questions from the audience?
I would have one, if I may ask a question. Igal, maybe you said it, but I don't think so. So we saw the connection between your concept and legitimate equilibrium, which is very nice and clear, I think. Do you know the connection between your concept and the optimistic equilibrium concept of Vasquez? What I recall from our paper is that it was very difficult to lay a very precise connection in terms of a theorem that would say that if this and this, then one is implying the other.
Well, let me repeat a point I already made. I'm not sure this is a direct answer to the question, but let me elaborate on one remark. Suppose you have the following game. There are a finite number of players. Each makes a request, and the highest request is granted, right? Yeah. So what's an equilibrium here? Ask for infinity, right? That's a well-defined probability. And why is that an equilibrium? Well, think about a player, and he contemplates asking for 1,000. He knows that the other guys are going to ask for infinity, so he's going to be outbid. So 1,000 will give him 0. 1,000,000 will give him 0. Any number will give him 0. So he's actually indifferent between his strategies, and therefore any equilibrium, in particular infinity, is the best response. So that proves the existence of this equilibrium. Now, thinking about that, when the player is contemplating any particular choice, he's pessimistic about what he'll get. He'll assume that he'll be going to be outbid. So the salient feature here is pessimism rather than optimism. And therefore, without checking the mathematics, I very much doubt that it will align with optimistic equilibrium. Does that make sense?
Yes, yes. Thanks.
Good. Anyone else? Please don't be shy. Go ahead.
So there's this concept of nearly compact continuous game by Harris, Stinchcombe and Same. So they're kind of looking at games that basically have compactifications, an extension of utility function, which are continuous. And some of the games you look like have like this kind of flavor, they're like missing points, no smallest positive number. And so do you know how these things relate?
Well, I guess they do not relate. And the reason is that in my notion, there is no structure to the set of actions. So there's no topology, there's no order relation, there's no measurable structure, nothing, right? So it's just any set. And any structure, if there is, comes from the solution concept. And you are not tied to any specific algebra. And that was the whole idea, to evade all these structures that are either imposed on you by the game, or you impose on yourself for whatever reason, even if the original game was a finite game. So that's another philosophical distinction that I should have mentioned, that here there's no use of any structure in the action set.
But I mean, you always get some kind of implicit, I mean, you can always do things, go to stone spaces, interpret all these functions as continuous function in humongously ugly large spaces, but they generally do not fit together nicely, which gives like these things like failure of Fubini's theorem. So I'm not sure if this proves that there's no connection, that you're not using it. Because I think what they're basically trying to find games where these techniques allow you to say something useful for this kind of games by going to larger spaces, but still do so in a way that everything fits nicely together.
Yeah, well, I'm not excluding the possibility that there is some connection. However, I somewhat doubt it.
Okay, thank you.
Okay, Don't see anyone raising hands. Any more questions?
Perhaps I have one. Igal, so when you mentioned that you have there is no structure in your notion of equilibrium, and another point you mentioned that we can consider all the subsets, the power set of an action set, because end of the day, by the Hahn-Banach extension, we can get to that we have a total extension, that you call it total extension. But it means also that somehow we are interested in the minimal algebra on which we have an equilibrium, because if we extend, we have many extensions, and all those extensions are equilibria. So somehow we are interested in these minimal elements. Do you have any results or ideas on this?
I don't. So the existence of a minimal algebra, of course, is interesting only in the case of an infinite set. No. I don't have any results on that. Let me just make this remark. My notion of equilibrium is, let's call it open to the right. So if you have an equilibrium and you enlarge the algebra, it's still an equilibrium. And in legitimate equilibrium, it's the other way around. If you have an equilibrium, any smaller algebra will give you an equilibrium, but a larger one will not. So it's open to the left, so to speak. Yes. That's an interesting difference between the two notions.
Perhaps I'm not right, but at first it seems that it is not 100% precise, because it can happen that you have an equilibrium on a certain field, when even you can have sigma additivity, or you have a sigma field and you have a sigma additivity and as an equilibrium in the equilibrium, and you cannot extend it as a sigma additive set function anymore. So a broader class of games, for example, to the
so Miklos, what kind of equilibrium are you referring to?
So you are talking about your best response, and you say that it is open to the right. I mean that it's in the sense that if you would like to, for example, if you have a sigma additive set function in your equilibrium for a player, and it can happen that you cannot extend it to the power set as a sigma additive one. So in this sense, you cannot, your solution is not open to the right.
No, you don't want to have sigma additivity.
Okay, that's just a remark.
So let me be precise about my remark. So take any equilibrium and now extend one or more of the strategies to a larger algebra in an arbitrary way. That's a new equilibrium. That's the result. And it's not a difficult result. You just look at the definition and you realize that enlarging the algebra does not break any of the equilibrium condition. And the nice thing about that, if you use Hahn-Banach, is that you can always extend it to the entire power set.
Great. Okay, Igal, thank you very much.
Thank you all for your very good questions and remarks.
We hope to see you all at